Well, welcome everybody to the focus group session today. We hope that you have enjoyed your lunch break and you are still motivated to continue the discussions of this conference that just started this morning. My name is Laura Talenspeiro. I am a researcher at the Environmental Science and Technology Institute of the Universitat Autònoma de Barcelona, where I lead the research line called Management of Resources for a Circular Economy. Okay, let me move. Okay, I would like to share two important news for you. The first one is that I will advise you to use the Google Chrome during the conference because it's supposed to be working better with the IT tools we are using. And then the other message I want to pass on you is that we are recording the session, okay? The title of the session, as you can see here, is Circularity Use of Raw Materials. The EU Green Deal aims to make Europe the first carbon neutral continent in the world by 2050, as some of you already know. Some of the actions will include the decarbonizing of the energy sector and investing in more environmental friendly technologies. The aim of the session today is to discuss about the nexus between raw materials and energy technologies and learn about how energy system models are working to consider raw materials and circularity in their models. So just before we start with the presentations, I would like just to share with you some of the input we receive from the attendees of this focus group. There was a survey that was circulated about people to people that was registered, and here are some answers. Okay, so we asked what was the motivation to join this session, and we see that people attending today is interested on the fact that it is not clear if there will be enough materials or sufficient materials to apply some of the low carbon technologies in all countries around the world. Some people also mentioned that this is an emerging policy area, and they refer to this European 2020 project, which it's good to learn of. Some attendees are interested in analyzing synergies between decarbonization and circularity. Other people mention the use or the integration of energy system modeling with input-output methods. And then some other attendees were interested because they want to understand better how to address the non-intended consequences of using resources from a more system approach or point of view. And lastly, some people mentioned they're modeling waste and wastewater management systems, and they like to know how this will affect the circular economy framework and the extraction of raw materials. Okay, another question that we asked to the attendees was if they consider, if they were aware of any energy system model that was including raw materials as part of their model. Almost 80 people replied that they didn't know. 15% of the participants mentioned they are aware of people working on this area, especially combining energy system modeling with input-output tables. And then we have some people referring to this project, which I was not aware of, I have to say. So thank you very much for this input, it's very valuable. I copied and pasted here the website of the project, and here on the right side you can see a picture of the report. So we'll be keeping an eye on that. So thank you. Okay, and we also ask how do if issues on circularity must be included in energy system models. And most of the people, as you can see here, they say they will strongly agree on including circularity in their energy system models. Okay, So we see that this topic is let's say, a hot topic. And we are happy that today we're having this 1.5-hour session to talk about it. Okay, so I will just start the introduction of the speakers this afternoon. We have two parts in this session. The first part of the session are these three presentations. We will start with a presentation from the Professor Gianandrea Blengini from the Joint Research Center of the European Commission. He's the team leader of raw materials there, and his team is supporting the analysis of critical raw materials that is also led by DG GROW. So thank you, Gianandrea, for your talk today. Then we will continue with Íñigo Capellán Pérez. He's a researcher at the Group of Energy, Economy and System Dynamics at the University of Valladolid in Spain. And Íñigo will talk about his experience in the project MEDEAS. We just closed, I think, December 2019. And he will also talk about this new project called Locomotion. So thank you also, Íñigo, for your availability and joining us today. And our last speaker is my colleague, Cristina Madrid Lopez. She's a principal researcher of the project Sentinel at our institute at the University of Barcelona. And she will talk about the work that we are doing in the project Sentinel to include raw materials and circularity. Okay, during the session, we have this tool called Slido. You can see the link here. And if you enter the code that you see on the screen, then you will be able to formulate questions, and then we are hoping to come up with some answers from some of the presenters later on, once they finish all the presentation. Well, so I think that's all so far from my side. I welcome you again for this session. I hope you enjoy the presentations. So that's all. So I will now leave the floor to Gianandrea.
Thank you, Laura. It's coming. I think I successfully managed to switch on my mic, which is already an achievement. And now I have to show my presentation. So thank you so much for inviting me and the JRC to give this presentation on some very recent work that myself and my colleagues have done. My presentation is quite long. I try to keep it short and move the slides quite quick. It's related to two big blocks. The first one is the very recent adoptions of the fourth list of critical raw materials for the EU. And then a foresight study that with my colleagues we have done to understand the role of critical raw materials in strategic sectors from now to 2030 and 2050. The starting point cannot be anything else than the same one that Laura has already mentioned, the EU Green Deal, announced 10 months ago by President von der Leyen, where we all know we have a very ambitious objective in front of us, which is to reach neutrality in terms of climate change by 2050. The good point I want to highlight is the clear statement by politicians that if we want to achieve this objective, we need the resources that are used in the technologies that we will have to necessarily deploy. This connection is quite tight to the resources and in particular to the critical raw materials that are needed to drive the change. And here I start my discussion on criticality studies by highlighting the role of governments and academia to work together and understand the criticality of raw materials. So critical raw materials are special ones, are very important to achieve given objectives and have at the same time the unfortunate characteristic to have a high risk of supply disruptions. So for these reasons, we try to understand the levels of criticality, and once we understand a list of critical raw materials, which are the materials in the list, we try to understand which solutions we can adopt by diversifying more the supply, by using more resource efficiency, by using recycling and circularity, by improving the capacity to substitute critical raw materials. The Commission have worked hard over the last 10 years, setting a first edition of the methodology of criticality assessment in 2010, used for the first list, slightly adapting that in 2013 for the 2014 list of critical raw materials, second edition. Then in 2015, a quite large team in the JRC, which I led, was in charge of deeply revising the methodology. I'm not saying the methodology was turned upside down, because this is not the case, but some substantial changes were introduced in 2015 and used for the 2017 list, and now for the 2020 list that was published on the 3rd of September 2020. There are two dimensions of criticality. One is economic importance. I don't even want to mention that. And the other one is supply risk. Supply risk is calculated with the equation you see in my slide, which I will not describe in details, otherwise it would take 15 minutes only to talk about that. Supply risk is mostly based on country concentration and on governance of countries from which raw material are sourced. A combination of country concentration and country governance give the backbone of the supply risk, which is trade corrected, then balanced using import reliance, and finally it is filtered using recycling and substitution indexes. So this, I think, is more relevant for you in the discussion today. Recycling is associated commonly to circularity. There are a number of indicators that can be calculated based on recycling flows. There was one that we have selected, which is called end-of-life recycling input rate, that we use in the calculation of the supply risk. So in pills, the more we recycle, or let me rephrase, the more we obtain from recycling, the lower is the supply risk. And this is bringing us useful information for understanding which materials to place on the list. The work we have done with a quite large team in the JRC, mostly in 2019, interacting with a large number of stakeholders, was to assess criticality of 83 candidate critical raw materials, most of which are metals of different types, base metals, precious metals, specialty metals, and so forth, many industrial minerals, but also common construction materials or bio-based products. So 83 is quite a long list of candidate critical raw materials, so it's quite a long work. Everything is fine, Laura?
Yes, yes.
Okay, because I hear some strange noise, but maybe it's only my audio.
We hear you
Now,
perfectly well.
yeah, that's fine. So sorry for interrupting my talk. So based on the criticality assessment mostly run in 2019, as I said, we have issued a very recent list of 30 critical raw materials for the EU. And this is the starting point for a number of policy actions undertaken by the European Commission, and for which we have recommendations to the member states. So this is the list. I invite you to download and read carefully not only the COM, which is a very interesting document, also containing an action plan made of 10 actions. I also suggest, if you are interested in the topic, to download the report that was produced in support of the list, where you can also see the changes that took place from the first list of 14 critical raw materials in 2011 to the current list of 30 critical raw materials. Criticality plots are the way we use to represent criticality. This type of representation make the work of the Commission quite visible and understandable. In this slide, you can see the red dots, which are above the two thresholds of economic importance and supply risk, which identify the 30 critical raw materials currently in the list. One interesting approach is also to try to connect dots on the criticality diagram and follow changes from the previous editions or from the previous 2 or 3 editions. So this is only showing changes from 2017 to 2020, but we are currently working also at giving visual representations through the raw material information system. The map of global supply producers is something, in my opinion, quite interesting, where we can see from which countries critical raw materials are supplied. Brazil for niobium, United States for beryllium, many from China, Australia, South Africa, Democratic Republic of Congo, and so forth. I'm quickly going through the slides just to highlighting some of the most interesting content of our reports. A second representation is the one trying to depict the countries from which EU is sourcing the raw materials that are needed in the EU. This is not necessarily the same map as the previous one. In fact, we have selections. So normally EU accounts for like 12-15% of global consumption. So in some cases we can choose countries, and so the list of countries is not necessarily the same as I said before. A map of Europe that we have produced is showing in different countries what is the current production of critical raw materials, and we have similar maps also to show deposits or facilities or anything that can support, let's say, an increased domestic production in the EU to limit excessive import reliance. In the report, you will find details that I do not want to stress too much now, showing different components of the supply risk, or the supply risk calculated more globally for any country or for the EU in particular. And you might go in details and see that it's not always the same. This becomes probably more related to the topic today, and therefore more interesting for you. This is the latest available figures about the end-of-life recycling input rate, which represent how much of the raw material we are currently obtaining through recycling. As I said, it's an indicator related to recycling, which is calculated on a methodology that you could find described in details in the dedicated JRC report that I am showing right now in this slide. You could notice that for some materials, the recycling input rate is quite high. For some, it's still an important one, and for many critical raw material, recycling is currently very low. Figures are in this slide, but they are just figures, so I'm not spending too much time on that. This recycling rate, end-of-life recycling input rate, is used in the monitoring framework for the monitoring of the circular economy in the EU. I'm mentioning in this slide the COM that let's say, published for the first time a couple of years ago the set of 10 indicators. This end-of-life recycling input rate, which is based on MSA, a particular type of material flow analysis run by the European Commission. These MSA studies are producing the information that is used to calculate this recycling rate, which is one of the most important indicators out of the 10 of the monitoring framework. Just to mention some more work of the JRC connected to the topics I am discussing about, I mentioned the raw material scoreboard. in which one of the indicators is based on the end-of-life recycling input rate. So in this slide, you have a periodic table, quite colorful slide, this one, with an indication of the current recycling rate. In the lower part, you have a bar showing those materials that cannot fit in the periodic table. The new edition of the Raw Material Scoreboard 2020 is ready to be published. If I understood correctly, should be out in October, end of October or November. However, very, very soon. Some other reports related to the topic are this one, critical raw material in the circular economy, where the JRC has studied in given sectors, highlighted in this slide on the right side, what is the role of critical raw materials in a context of circular economy. I'm trying to go quite quick to keep the time. Another report that might be of some interest, also tightly connected to circular economy, which was announced already in the COM of the Circular Economy Action Plan, is the report related to recovery of critical and other materials from mining, waste, and landfills, which I also invite to consider. So I'm jumping onto my second big block, that is the foresight report that the JRC has published in parallel with the study related to the list of critical raw materials. This is being considered quite an important report of the JRC, and this report, at least the summary, has been used widely by Vice President Maroš Šefčovič immediately after the release of the list to highlight that based on this modeling that the JRC has done, by the year 2030 and 2050, we might need up to 60 times more lithium and 15 times more cobalt just for batteries in the EU. So this is quite important also because it was widely disclosed to by high-level politicians in the EU. It's connected to what we know from other bodies like OECD, explaining that we will certainly double very soon the already huge consumption of raw material of any types. This is not big news, but what I want to highlight is that it's not just the change in terms of size of quantity, it's the type of the raw materials that we will need, which makes a completely different picture. President Šefčovič is highlighting as well in his press release that we do not want to change the current dependency on fossil fuels with a future dependency on foreign import of critical raw materials. So this is also a very tough statement from Vice President. The competition internationally is announced to become more and more tough. And there are many different types of competition. So in some cases, we also have competition not among countries, but among technologies. This is the content of one of the recent reports by the JRC, dealing with the dual use of the same critical raw material in in technologies that are used for civil and military purposes at the same time. So I have a few slides that I'm passing quite quick to highlight which raw materials or critical raw materials in these slides, the critical raw materials are red, are used in key technologies. So we know about batteries and the importance of traction batteries, and therefore we are talking certainly about lithium, graphite, cobalt, and many more. Then we can move to magnets and therefore electric engines or wind turbines, and we are basically talking about rare earth elements. So I could talk one day about that and the role of China and other players. Solar PV, it's much related to silicon metal, but also gallium, germanium, and indium, of course. In the JRC report, you could find interesting representations like this one, highlighting for the 9 key technologies that we have studied, which are the 30 critical raw materials used here and there, associated in the lower part of my slide with the related risk of supply interruptions. You'll find as well very colorful graphs like this one, highlighting on the right side the 3 sectors that we have considered, the connection with the 9 technologies I mentioned already before, and with the list of critical raw materials associated with blocks of different colors corresponding to the different risk of supply interruptions. In the graph, in the report as well, and I'm getting very close to my conclusion, you find our forecast for 2030 and 2050 according to high, medium, and low demand scenario. I just want to highlight that the high demand scenario would mean that the Green Deal is working. So we are effecting in deploying technologies and in achieving the goals. So one might consider this is a pessimistic scenario. It would be pessimistic in the sense that we would need so much materials that we really do not know whether it will be really possible. However, it's not a pessimistic scenario, it's an optimistic one. And so you have my slide for conclusion, which are not my conclusions, but are the conclusions just taken from the press release of Vice President Šefčovič. So first of all, an highlight, not by myself, it would be very easy if I underline the importance of raw materials, and most of the audience today knows how raw materials are important. What's important here is that are the politicians that are saying that, which make a huge difference. So they are important today, and they will play an increasingly important role in the near future and in the future. In the next future. Second element, we need a secure and sustainable supply of raw materials and critical raw materials. You might have noticed that the content of this speech is very close also to the executive order of Donald Trump published on the 30th of September, which was also commented by newspapers very, very recently. So we need to make sure that supply will be there and will be secure and will be sustainable at the same time. We unfortunately need to acknowledge some sad reality, and the reality is that this is particularly tough. So we have some problems in Europe in particular about excessive dependency from foreign supply, often from countries where we have low governance and therefore bad environmental and social consequences. Luckily, we have an action plan in the EU related to critical raw materials with 10 points, and based on these 10 points, we will be able to monitor progress. One last point, and then I close. Again, taken from Vice President Šefčovič, is highlighting the importance of reuse, repair, recycling, and also resource efficiency in achieving these goals. And with this, I stop my presentation.
Very much, Andrea. I like very much how you mentioned that this transition to a low carbon economy may imply this critical raw material dependency. And I think that's exactly what we want to talk during the session today. So thank you very much, Andrea. I will pass now to Inigo.
Okay, thank you very much. Thank you very much for the invitation. It's very interesting, this session. And in fact, also the presentation of Jan and Andrea was also an excellent introduction for my talk, because I'm going to talk about what we have done in the MEDEAS project, which finished last year. In that project, we were, my group, the group of Energy, Economy and System Dynamics of the University of Valladolid, we were in charge of the modeling of a new integrated assessment model And now we are the coordinators in the ongoing project Locomotion, which main objective is to continue developing this MEDEAS approach. So first thing I would like to say is that in our group, there was nobody specialist in materials, but we reading this kind of documentation and reports that Gian Andrea was overviewing, we got aware of the importance of this, and then we decided to build a specific module to be connected with the rest of the model and very tightly connected to the energy module to be able to analyze all these factors which Gian Andrea was mentioning in a dynamic and integrated way. Okay, so the context of our research in general in the group is that scaling up renewables to 100% has diverse and very relevant implications outside of the energy system. No, so here these pictures are very self-explicative. We can talk about investments in the economy side. We can talk about land and biodiversity. We can talk about materials, etc. So today I will focus on the materials. So before focusing on this specific part of the model, I just want to give you a very brief overview of what is this tool which we have developed, which we call MEDEAS. This is the structure of the MEDEAS world model, the global model. And basically you can see that each box, I don't know if you can see my mouse. Okay, I will show it anyway.
Yes, we do, Inigo.
Okay.
We can follow that.
Thank you. So each module, each box represents conceptually one module, no? So here with this figure, we can understand more or less what is happening. First of all, we have a demand, economic demand, because we have a demand-driven philosophy. So we do not have a GDP per capita or GDP as driver. For us, GDP is endogenous, is the result of the economic activity. But what we do have as driver is the demand, what people are demanding. And we have here some input-output to transform this demand of final users into the production. And then we get a demand of energy. And then we confront this demand of energy with energy availability, energy supply, and we get some level of energy consumption, and energy mix, installation of new capacities, and these kind of things. Depending on the energy infrastructures which we install, we have dynamically integrated the requirements of minerals. So here we have the module of minerals, and of course, energy infrastructures require minerals, but the rest of the economy also require minerals. So we have made some assumption to account also for this. Finally, depending on the energy consumption, we get the CO2 emissions. We have a small climate module transformed to temperature, and we have some damages. So here we have several feedbacks. A very interesting feedback which we have due to the fact that we are accounting for this material extraction is what we call the ROI feedback. No, so it's very interesting that energy models account for additional monetary investments typically, so in terms of learning curves and so on, but they don't account for the additional energy investments. So what we do is when we do the transition, we need to do monetary investment, but also energy investments, and this reduces the energy available in the society. So the system can react in different ways. We model it increasing the total energy supply in order to cover the same level of net energy as it was initially demanded by the population. Okay, so this is just very brief. Okay, so the rationale for integrating materials in the model, I think Gian Andrea explained it very well. I don't need to go further. The transition will require, the energy transition will require a higher amount of materials and a higher diversity. And this higher amount of materials, we can understand it well if we go to the physics of renewable energy. Renewable energy is dispersed energy. While fossil fuel are concentrated in deposits. So when we compute, for example, in this figure for different energy resources, the watts per square meter, what we call power density, in very small amount of land, we can extract a lot of energy. But for renewables, depending on the renewable, of course, biomass is the less efficient in terms of land use, and photovoltaics is the most efficient. But here we have the thermodynamic limit. We cannot extract with solar more than the solar irradiance. This is a kind of global average. So we have here a biophysical limit, which makes that the renewables, in order to collect the same amount of energy, we are going to need more infrastructures. This is, let's call it physics. There are more factors which are going to go in this direction. And another factor which is quite intuitive is that the fact that the capacity factor of renewables is always lower because they are not dispatchable. So the capacity factor of solar, if we have day and night, is not never going to go over that threshold. While fossil fuels, if you have it already stored, you will be able to burn it. So because this graph is in terms of installed capacity, if we talk about generated electricity, we will have to reduce these gray boxes to lower them even more. And then we have another biophysical factor, which is the fact that the renewables are variables. So we need to set up some systems, additional system to manage that variability, okay? So we can think about the storage, we can think about grids, conversion, and etc. So some relevant questions which appear in this context, no? For example, which amount of which materials will the transition to sustainable energy systems will require? How much of these materials will come from recycling? How much of the materials will come demanded by the rest of the economy, because we are not in an isolated system. So if the economy is using more lithium for mobile phones, there will be less lithium for electric cars. So this is like that, and we have to take into account that. The identification of the potential critical materials. So Jan Andrea has explained the approach of the group in GRC, but we can also think about other definition of criticality. We, for example, for simplicity, we just compare the cumulated extraction with reserves and resources. So for us, criticality is just a reflection of, let's say, geological availability. We do not put in factor the factors that are taken account in the GRC works, but they are complementary. Also, another relevant question, the substitutions, which also was mentioned before. Which substitutions are possible, and which are the trade-offs of these substitutions or advantages? And finally, we can also push this a bit further, because all these minerals, which most of them are not in the economy, will need to be mined even if the recycling rate is 100%. They need to enter the system. So this is going to have a great socio-ecological impacts. There has been recently a published study about this. So a very quick overview of the literature shows that most of these topics are not being really addressed. Just the first point of how much materials for the energy system is, there is a research, and also the identification of the potential criticality of materials. My view on this is that most of the work is what I call impact analysis. So it is not dynamic. So here we are in a conference of energy modeling. I think we all know the advantages, and we are aware of the advantages of the dynamic modeling versus static impact analysis. No, so the modeling will bring a lot of insights which static analysis cannot bring, such, for example, the dynamics of extraction, substitutions, the fact that lifetimes are not fixed. If the batteries are used more intensively, their lifetime decreases. You need to change more often. As I said, the demand of the rest of the economy is also dynamic. Also, there are dynamics very interesting coming from the materials side. For example, this maybe is new for some people, the fact that when the ore grade of a resource decreases, here, for example, is an example for copper. So here we have a concentration of 2%. So in 100 kilos of ground, there is 2 kilos of copper. And when we go down to the concentration, the energy required to extract this increases exponentially due to thermodynamical limits again. So there are some studies showing that for some minerals, we are already here, or we could arrive to this situation with huge levels of cumulated demand. So this will pose again a kind of feedback in the system when we are going to need much more energy just to process materials. Okay, so we will need to upscale the energy system just to be able to run it. Okay, here I have made a very quick review of the models, which I am aware that included these kind of materials in a dynamic way, but I already saw in Laura's presentation that there was one comment about one project also who is doing this EU calculator, so I have already noted down, and in the focus group later in the group, we can talk more about this. So here I'm going to focus a bit on MEDEAS. Laura, can you tell me how much time I have? Sorry, because
I will leave you 5 more minutes.
Okay, thank you.
Okay.
Okay, so what we have done in MEDEAS, as I said, we are in general people coming from the modeling of energy and economy, and we were not aware so much of it. We didn't have specific knowledge on this. Now, after 4 or 5 years, we are having some getting some experience, and the approach was twofold. Like from the one side, we got an inventory approach for the energy technologies for which we were able to find good data, let's say, like material intensity. We were looking for kilograms per megawatt of different technologies. So in MEDEAS, what we have is for these technologies, solar photovoltaic, solar thermal, wind onshore, wind offshore, lithium batteries and grids, electrical grids to connect these additional power plants. We checked what were the requirements in terms of minerals for this set of minerals, okay? So, and then for the rest of the economy, we did some assumption, very broad assumption, taking as driver the historic data and the relation with GDP per capita. So GDP per capita and historical demand with the data from USGS. So like that, rest of economy plus energy system, the addition gets the total. Okay. So data challenges that we found, and we can also discuss that, it's very difficult to find data for sub-technologies. As you know, for solar PV, you can have thin film, you can have silicon, poly, multi, etc. So, but this is very important for substitution to model this sub-technology diversity. Also, it's a problem the openness of data in MEDEAS because the model is open, and in locomotion also we couldn't rely on some database which are not closed, so we need to find the data elsewhere. Okay, all this is documented here in this paper in the supplementary material. So if anybody is interested into taking a look, here it is explained, and because the model is open source, you have also all the data. And then the second point, once we have all the data, is the dynamic integration with the rest of the model. I think I already explained this more or less, the connection with the rest of the economy. Then we integrate the recycling rate, so we distinguish between demand and primary demand to be extracted from mines. We also have the dynamic demand of storage to manage the renewable variability. And then we also have this ROI feedback, which I mentioned, which takes into account that you need to make energy investments to do the energy transition. No? So the link is direct because the denominator of the ROI comes from the multiplication of the material intensity and the energy required. And this is documented here, if anybody is curious. Okay, so just I didn't want to finish before giving some results of what kind of outcomes we can get with this model. So I'm going to show you results from that paper that I just mentioned, in which what we did was to test several scenarios. And here I'm going just to show results about the one scenario, global scenario, in a storyline of green growth. So more economic growth, more efficiency, transition to renewables, transition to electric vehicles, efficiency, etc. And reaching 100% renewables in electricity in 2060. Okay, so more or less in the line of what we should do. Okay, so this first table is how much will the demand increase for these materials for energy technologies comparing for the rest of the economy. So, for example, this means that following our results, the demand, for example, for zinc comparing with the expected demand of the rest of the economy will be small. But for example, for this in red, aluminium, cadmium, copper, gallium, etc., we estimate that the demand for energy will more than double the demand for the rest of the economy. No, so this is very interesting. And then what we do is to compare with the levels of reserves and resources. As I said, it's like kind of an indicator of mineral geological criticality. So here, for example, what we compare in this figure, the scenario 100% renewables is the black bar, so ignore the others, which are scenarios which are less ambitious. So here, for example, we find that the cumulated extraction for renewable technologies, comparing with their reserves, will be larger for minerals such as tellurium, indium, tin, silver, and gallium, okay? 60% of lithium and so on. And then if we compare the total extraction, so renewable energies plus rest of the system with resources is an indicator that tells you it's an estimate of how much is below the ground, but it is uncertain if that is going to be extracted or maybe there will be more discoveries. This is subject to great uncertainty, but the number is always bigger. And here we also find problems, potential problems in indium, tellurium, silver, and very high shares for others like manganese, molybdenum, or nickel or copper. Okay, so this is the last result. In terms of ROI of the system, so how much energy is returned by the energy system and how much energy is invested, here we can see very good this valley corresponds to the peak in the installation of new systems. So it's very clear that as the faster we do the transition, more energy, more net energy is drained, is diverted from the system, from society, let's say, from final users to fuel this, literally fuel this energy transition. No, so this is an interesting result, which now in locomotion we are planning to feed back through the economy module, through all the investments and so on. So this is going to be also challenging, but okay. So these are my conclusions. Like these results show basically that confirm the static analysis in the sense that we find several materials which could be critical in the future. We also calculate the fact that the recycling rates, even if they are very high, for some metals, this is irrelevant because they need to enter the system, so they need to be mined. Then also the socio-economic and environmental impact of the new mines is something that is almost not researched. There is this recent paper which I recommend, published very recently. So just to finish a bit our philosophy in the group, in MEDEAS and Locomotion Project, is that sustainability is a multidimensional concept. So it doesn't make too much sense to analyze separately. So the objective, of course, is very complex and very challenging, but the objective should be to integrate all the relevant sustainability dimensions in order to achieve robust policy advice. Okay. Sorry, I have some limitations on further work. Well, I think I mentioned them already. I mentioned linked to already to Locomotion Project, so not to make it longer. Thank you very much.
Okay, thank you very much, Íñigo. I think your presentation has been very insightful. I think you put on the table also some interesting issues. I like very much this graph that you show the power density, and how in physical terms there's a limitation due to this power density of some energy sources. Okay, we are running a bit late, but I will still like to hear Christina's presentation. I'm just gonna jump to her, and then we'll continue. Okay, Christina, you should be able to get a link now. You're the presenter, so the virtual space is yours. Thank you.
Thanks. So thank you everyone for coming. I have to make a fair warning, and it's that I have a terrible cold. And it seems that we have still 1,000 bugs apart from coronavirus, and I got one of those. So you might hear me a little bit low today. Very briefly, you will see that our presentation is very much aligned with what Inigo and Gianandrea had been presenting today. I'd like to show you a little bit the work with raw material and circularity in energy models in this case, and the challenges that we met when we were trying to model raw materials or circularity, and some next steps that hopefully will be a launcher for the further discussion later on. So let me just tell you that this is a work that we are doing together with Laura, who's the host of our session, and Nick Martin, a colleague who's working with us in Barcelona. And then this is part of the project Sentinel, which is a project that has as an objective to create a platform for connecting different energy modeling initiatives. So we are within this work package 2. We are developing the module Enviro. Enviro is a module to assess environmental and resource constraints of different energy system configurations. We are looking at questions like, is it feasible? Can we say if this is good or bad? These are very heavy questions. So pretty much in the development of this task, we met some challenges, as I'm sure you all have. And that's how I will say that we are not talking about raw materials and circularity models today, but specifically to those that we have met in the development of Enviro. So first, allow me to just explain you how we include raw materials and circularity in Enviro, or what is Enviro and how it looks like. So pretty much we get energy system configuration coming from some colleagues in the project, and we identify what we call relevant processes, which are actually a set of technologies and the upscaled sectors that are using them. We will then calculate many different flows, including greenhouse gas emissions or water use, but specifically what is interesting for today is this raw material, associated raw material flows. And for that, we are using both some life cycle assessment data, mostly inventories that I'll describe later, and then some data from what we can call a metabolism, a social metabolism framework. And from this calculation of flows, then we estimate 2 types of indicators, if you want to call it that way. Some indicators are related to the life cycle impact assessment that will answer questions like, what impacts does the use of raw material produce? And then some indicators on metabolism, which are telling us what we do with those raw materials and how are we using them. And then how do we do the upscaling, and how do we assign responsibilities for the use of raw materials among different sectors. Now we combine those and compare them with some benchmarks, and then we have what we call the Enviro constraints, which will then be fed to other colleagues to, let's say, limit the option space that we can have as a configuration for a sustainable energy system. So let me be a little bit more specific. I'm going to talk to you about the inputs and outputs regarding raw materials and circularity in Enviro. So raw materials inputs are coming as data inside our calculation of flows. So far, I'm going to show you later a little bit more on that, but we have compiled a library of about 540 inventories. That has been a nice job by Nick. And then we are including, of course, new, or we try to include not only main databases inventories, but also try to include the new life cycle inventories for renewable energy systems. And I show you some publications that we have consulted, for example, and including some studies on key raw materials of one of our attendees. Regarding circularity, that would be more the part that we deal with in this metabolism part, right? So we include end-of-life scenarios. that are within our already, so we try to incorporate these scenarios within our existing life cycle inventories because they are usually not considered, and we try to improve our data input with those. So this is just like a side of how our library at the moment, and hopefully growing. We try to use databases registered in the Global Lifecycle Assessment Data Access Network. But I have to acknowledge that so far, the most important ones have been EcoInvent and Gavi. You can see here the numbers in yellow and green in the photos. And for each of these categories, in green, you can see the type of technologies, or in blue, you can see the geographical locations, and in black, you can see the years of reference. Now, in blue, in light blue, you can see that we deal with supply technologies, also demand technologies, and we also look at the electricity supply with, let's say, our unit of reference in megajoules, which would be the consumption or the supply of electricity. Now, so this is our inputs. Then we model, or you could call it that, or we do our assessment. And what are the outputs that we are aiming at getting? So we are aiming at producing 4 types of indicators that are relevant for raw materials and circularity. One of them would be a contribution to the cumulative resource use that we have been talking about. Another would be to contribute to improve the efficiency indicators, comparing total resource use versus energy output and considering even energy input as well. Different indicators that have to do with supply risk and that have been I wouldn't want to say in fashion, but I have been an ongoing work, right? You can see here some examples that we have consulted. And also we are aiming at providing indicators of robustness of the system against circularity, against, not against. Against means about circularity in this case. So in that task, we are finding some challenges, of course. One of the objectives that we have in Enviro is to make a useful tool. And this is why we also organize this focus group. And I hope that you join later on the subgroups. So we found 4 types of challenges. One of them is shared by Inigo, I see. These are regarding availability of data, format, sources, openness of the data. Another type of challenges that we met, that we found, are how to compute raw materials on circularity, topics of substitution, how to do this upscaling, sorry, there's a typo there, how to do the upscaling, and these other topics regarding metabolism that I commented before. Another challenge that we met is how to make it policy relevant, right? How to make it not only policy relevant, but how to be sure that what we are, the results that we are contributing are robust enough to advise policy relevant in an uncertain climate. How we define the targets, how we do harmonization, how to check coherence between policies, something that also Jan Andrea mentioned before. And then how to integrate, for example, different, sorry, I'm in blank, with energy system models, the relevance, the limitations, etc. So I would like to encourage you to join the discussion subgroups in a couple of minutes. And just for you to know, in case you might find Enviro interesting or want to reach out, so we are improving the Enviro design started with the coding already because it's going to be a software tool. We constantly adapt Enviro to user needs. So far we are working with models like Calliope and other similar ones, but we are happy to hear from you if you have specific needs. We have also run a couple of workshops to gather information about that. And we are going to be using them within case studies in Sentinel to see it in action and to test the pilot. So maybe some food for thought. I think some points are shared with Inigo, so I won't go too much into them. The low carbon economy type of policy still relies on limited sources. The circular economy, even though we aim at closing the loop for key materials, still rely on primary material sources. The availability of raw materials and new technology data with a specific formats, will be perfect to do integration between environmental models and energy system models, in this case like life cycle assessment or others. And we would like to have a higher, or we would like to see a higher use of energy and water constraints in the development of prospective future scenarios, for example, that reflect on the degradation of our grades, something that also Inigo commented on. So we are working on these more robust indicators, including the ROI with a life cycle perspective, of course, and then issues like supply risk of cumulative resource use. I think this is repeated. So this is all from our side. I hope we have a fruitful discussion, and that's it. I can give you the floor, the virtual floor, Laura, again. Thank you.
Okay. Okay, thank you very much, Cristina, for your presentation. Okay, so thank you very much for the presentation as well, Cristina. Okay, we're a bit running out of time, I'm sorry, but I just thought that the presentation were very, very interesting, so I prefer to spend a bit of more time on that. So now you can do, I have seen there's some already questions on the Slido, so I will just read some of them and leave a few minutes to comment on them, and then we'll move to the subgroups. Okay, so the first question is from Philip Nuss. Hello, Philip, and is for the GRC. I'll try to make it bigger. So the question is, have you looked at by how much the end-of-life recycling input rate could increase for materials under EU circular economy scenarios, in brackets, during the economic transition towards climate neutrality? I know it's maybe not easy to answer a question right now. So I'm
Do
not
I
sure
pick it
Andrea.
now, Laura?
Yes, if
Laura.
you can react on that.
So provocation. So why increase and not decrease? Because honestly speaking, given it's for many of these, I mean, the key critical raw materials for the key technology we have seen are not always very much recycled, or their contribution in terms of secondary materials to satisfy demand is quite low. So in the future, we can expect any change, including decreasing even further, because if demand is growing so much, we have seen the case of cobalt. So cobalt, calculating recycling input rate for cobalt has been really challenging. So we had to interact with many stakeholders, with industry, and it was really tough. And it's currently around, let's say 20%. But if cobalt is going to increase 50 times, it will be complicated even to maintain a contribution of 20%. So I'm sorry to react not totally positively to this one, Philip, but we will see. But the question is good. So is Commission launching studies to understand this? This probably we are not deploying enough resources in this sense. So we should dedicate more effort, more people, more budget. So also some European projects in the future should focus on that one, because we need information. It emerged also in the presentations. I didn't emphasize anything about data, but Maria and Inigo said that clearly. The problem is about data. When it comes to recycling, it's 10 times more.
Yes. Yes, I think that indeed data is one of the things we want to discuss on the subgroups that we are launching just after we close the question and answer session. Okay, thank you very much, Andrea. Okay, there's two questions to Inigo. The first one from Diego Garcia. It's saying, have you considered the economic effects of substitution of critical raw materials in a dynamic way? I mean on GDP in a sort of endogenization? Thanks.
The answer is quick, no. We had many troubles to find a way to estimate this rest of the economy, because there are many analyses which only focus on the impacts of the energy system to increase the demand of materials. So, as I said, in order to see the geological risk, you need to have the whole picture. So we didn't found data about this, and also to model substitutions in end use sector means that you need to have your end use sector modeled very much detail, bottom up. So for example, that we can do, we are going to do in a new project, a substitution in energy technologies, energy generation, and transportation, batteries, and these kind of things. But then to try to model all sectors bottom up, for the moment, it's out of scope for us, and I think for the state of the art.
Okay, the second question is, what assumptions for material demand from the rest of economy? Energy return on investment based on geological scarcity, or takes into account energy in industrial refining processes, I guess.
The demand of minerals, okay, here I should distinguish. We are only estimating the demand of minerals from the rest of the economy. So we are not estimating the demand of, I don't know, concrete, sand, just minerals. And what we do is very simple. We took the data from USGS of primary demand, recycling rates, and like that, we estimated the final consumption. And we did some regressions with GDP per capita, all that at global level. And just to see what happened. And the regressions were very good. So we use this as an input, but it's very simple, very stylized. And about ROI, I don't understand based on geological scarcity.
Yeah, I think he's asking if the energy return on investment is based on geological scarcity, or if you're taking into account the energy in industrial refining processes.
Industrial refining process.
I think it's a bit tricky.
So this figure which I showed about the example of copper, this thing we are not modeling in MEDEAS, but we are planning to do it in locomotion, for example. Maybe I mixed the two projects, and even if I used too much time, it was not clear, but.
Okay, no, I think, yeah, I think also the question is a bit tricky. I'm not sure if he's asking. Okay, and then the last question I will take is the one for Christina. It says, how do you consider the dynamics of life cycle inventories regarding changes in flows happening when energy configuration varies through the years? Double counting, and then I see that Christina reacted, under which criteria or functions you modify life cycle inventories, and afterwards, if that affects the energy systems in an iterative manner. I think he's basically asking, Christina, if we are considering some dynamics on the life cycle inventory so far, and if so, how does it work?
That's what I understood too. So Diego, thank you. But Enviro is not meant to be neither a dynamic model nor a model itself. So it's more of a module that energy models can come back to check the results. So we are developing a static view for a year so far, and then we won't return another configuration of the energy system. We will just say, these are your, if with the configuration that you're giving us, these are your bottlenecks. This is the paths that are going to be problematic for you. And then it's up to the energy models to try a different route. I hope that is the question.
Okay. Now you are all welcome to join. We are having this subgroup discussion. We are, as I said, a bit late on time, but I'm hoping you can spend a bit more time today with us. So we are having this subgroup discussion, which will take place using the B2 match. If you go to, I think here I have some slides. If you go to your agenda on the conference website, you will see that there are some subgroups described here. The way to join one of the subgroups is to add, in case you haven't done yet, and then to click on this icon which says join online session. So once you enter this online session, we will have access to a board that we are using with a software called Miro. And this should allow you to interact with the rest of the people on the discussion group. The way you can interact and you can offer your input is by using this kind of sticker icon here, sorry, that you just place on the board, and then you will be able to edit your comments. Okay, I will just let me see if I can stop sharing. I'm just about to post. Let me see. I'm sorry, this is a bit confusing sometimes. Okay, I'm just about to post the links to the subsessions just in case somebody didn't manage to get on their agenda. Okay, so I'm hoping you can see that there. Here are the links. And as you enter your subgroups, you will be able to see a link to this Miro whiteboard where we are hoping you to provide some input. So the idea is that we close this GoToWebinar now, and we all move to the subgroups. And then I will ask you to be back at 10 minutes past 3 to do a very short wrap up if we still have some time and if you are motivated to do so. Okay, so I would just close. I thank you all the participants to join the presentation so far, and I'll invite you to join the subgroups discussions, and I'll see some of you there if you're going to Group D. I know Nick Martin, who happens to be our colleague at ICTA, will be leading the discussion in Group A about data availability. Íñigo Capellán Pérez will be the coordinator of Group B, discussing about the computation of raw materials and circularity. Cristina Madrid is the coordinator of Group C on policy harmonization, and myself, I will be in Group D. So I close this for now. I hope to meet some of you on the subgroups. Thank you again, and thank you also for the speakers for all the presentation and very interesting information. I think it's been really useful, all the information we have been provided even today. So, okay, I'll see you in the subgroups. Thank you. Hello.
Laura.
Hello. I have to say that this is the first time we are trying this, and this has been a real challenge, moving virtually the space. Okay, I was hoping to get more input from the boards. But the good news is that we have new people working on this area. I think these are very good news, as there's more effort need to be done. So I think that's one of the very positive message we can take. I think that next year we're gonna have again the same conference. This is organized by the European Commission annually. And of course, we're gonna have another session on raw materials and circularity. And hopefully we will gain more input from other researchers and institutes and collaborators. So I think, I don't know if you want to add anything, Gian Andrea and Inigo. I invite you to add any comment you would like to have for the closing of this focus group.
Laura. No, well, if I can, maybe a comment I can share is that, well, you know quite well what we have done in JRC, Laura, because you were working with us, and you know the problem we had when you have to deal with a large number of materials, and they are used everywhere, and everything you want to do must be, you have to do it for all of them. I hope we will get soon out of this situation where the focus can be narrowed to some groups for dedicated sectors or technologies, and then we can go more in details and start advancing a little bit further. So you know very well how simplified is the methodology of criticality assessment, because it has to be applied to 83 candidates critical raw materials, including metals, base metals, and industrial minerals, and even bio-based, which is anything you can imagine. So this is something I really hope is happening. And then when you start modeling, you don't have to accommodate at the same time wood and germanium, which has nothing to deal with one another. And when you come to circularity aspects, you can really start to understand something better. So this is a message I want to pass. So while I was listening to Inigo and Cristina, I was, let's say, feeling some envy, because they can work as researchers, and I work as a mix of research and support of policymakers, which is completely another story. So they can use fantasy and try to understand whether it works or not, and that's much more exciting, I think. People in JRC are using science to support policy, so it cannot be something you invented yesterday. It has to be bulletproof, something that, because you have seen the messages of the politicians, so they build on what you say and they can say anything, so it's risky business. I hope it's a useful comment at the end of.
Yes, I think it's very useful, and I think actually that's a bit real life, yeah. So there's research, and then there's the implementation of some research results and methodologies, and that's not an easy job, I have to say. So, okay, I think it's a nice message. I'm not sure if Inigo wants to add as well something, and then Cristina.
My very short comment is that this session showed that we need to work together, people from energy models with people from circularity of materials, which until very recently they are communities very, I think, separated. So we need to build that bridge, I think.
Yes, yes, indeed. Yes, indeed. That's well, I have to admit that also us as a research team, we have faced that. If you want to have all this overview on the impacts of raw materials in energy system modeling is, yeah, it's not easy, and it's not immediate. So yeah, collaboration, yeah, it's needed, and more people. But I'm happy, as I said, more people is joining. New people. We have probably new and more information next year. Cristina, any comment before closing the session?
Yes, maybe a thought, and is that being me myself not a critical raw material or raw material expert, my take is that it is a topic that everyone can see how important it is. I don't think anyone can deny that it is important. And I am hoping that we generate expectations and that we can reach to energy modelers to make that switch and see how important this is. And hopefully we are all careful to not to create a buzzword with these critical raw materials, but that we do robust analysis that are actually useful, because all the other keywords come to mind, like nexus, or that sometimes are a little bit dispirited, right? So I'm hoping that we can all see the relevance it has, because it has a real actual relevance. And actually, I just wanted to say thank you, Laura, for all the organization of these sessions. It's been a lot of work that no one can actually see, but it's been quite a lot of work, and you did really well. So thank you so much from the whole group.
Okay. Well,
for the
thank you for
organization.
all your time and participation. Without you, it would have not been possible. And I was very happy to put the three of you together this afternoon. So thank you very much to all of you. And we'll keep working and in touch. And I'm hoping you can also follow maybe some of the other sessions of the EMP conference. And that's it for today. So thank you so much also for the participants to follow the discussions. I'm sorry that that we had some technical limitations with the different tools we are using. So this is something we have to improve next year, and we'll be doing that for sure. Okay, so thank you very much. Take care.
Thank you
Have a
so
good day.
much.
Thank you, everyone.
Thank you, Laura.
Nice to
Bye
have you.
Bye. Bye.
Bye-bye.
Bye.
Bye-bye.
Bye-bye.